All right, so in these examples, we are given the Q3 score and the SOV scores for the same predictions. The first line is the correct secondary structure state, and that would usually be listed in the PDB file. All right. There are also programs that can look at the three-dimensional coordinates of the amino acids and tell you what the secondary structure states are. And I'll show you that this is not a ground truth. I mean, people still disagree on how secondary structures should be defined or how they should be extracted from the PDB files. So even if you know this tertiary structure, people still disagree on how the secondary structure should be assigned. Okay. But let's assume that this is the correct secondary structure sequence that we are trying to predict, and we are given 5 predictions. Okay. So in the first prediction, you have a mixture of coils and helices. In your correct secondary structure, you have a single helical structure, and then you have a coil residue at the end. Okay? So as far as applications are concerned, such as assigning this protein to a structural family or figuring out how it falls, it's more important to predict that there's a helix here than to predict the exact state of each residue. Okay, so if helices are together like this, that's a better prediction than this prediction 1. All right. Okay, so if you look at the Q3 scores, which doesn't really take into account the segments of secondary structures, it considers individual residues. Their scores are the same, but clearly the prediction 2 is a better prediction. The SOV score takes into account these segments. Okay, so not only you want the correct state, but you want also sort of the segments to overlap. All right. So it has a higher accuracy. It gives a higher score to the second prediction compared to the first one. So long as you are predicting that there's a helix here, it doesn't really penalize as much whether you are able to predict these ends correctly. All right. So I'm not going to code this completely because this is one of the more involved implementations, and I don't have a MATLAB file for it yet. But I'll just give you the main idea. So let's say we have a correct secondary structure state and a predicted sequence. So what you need to do is identify these segments, right? Or identify the number of times that they overlap and the number of times that they are different. Okay, so let's look at the helices first. It helps if you define logical indices for the locations of secondary structure segments. So let's say SS equals a helix. All right, and let's do the same thing for the prediction equals helix. Okay. So as a very simple measure, what I'll do is I'll just take the intersection of the two and divide it by their union. Okay. So the intersection is going to be SSI and PPI. So if you have two logical vectors, and there are some ones here, and there are some ones here, let's say, and let's say the rest are zeros. This single AND operator takes two vectors. It's very similar to the double AND operator. Double AND only works on single numbers, but the single AND operator works on vectors, and it'll give you a new vector. So if you AND these two, you'll get a new vector where you will have zeros everywhere except where you have ones on both sequences. Okay? So if there's a single one, you get a 0. If there are two ones, one from each sequence, you get a 1. So this will be the output of this ANDing operator. So that'll give you the intersection of the two vectors. All right? If you want to get the union, you can do a single OR, and that'll be the same thing. You'll get a 1 if there's at least 1 in these two vectors. Okay? And you can use the NNZ function to count the number of times that you have a 1 in here. So that'll give you the number of times that the two assignments match, or the prediction matches the correct output. And this will be their union. Okay. Then you would just divide them. And let's say we return this. In the actual SOV score, you need to repeat this for coils and sheets, and you also need to multiply it with a factor that is sort of a scaling factor that takes into account the length of these segments. Okay. All right. So I'm just going to leave this function as it is like that. All right. So we have our sequences, and we have a way to evaluate the accuracy of a prediction. In order to train a neural network, we need to encode both the input and output. Okay, so we need to have a numerical representation of these characters. Let's say you have an amino acid sequence like this. All right. One way to encode this numerically is to just convert it to their integer representations. Right. So you have AA to int, and you get numbers 1 to 20. Let me change this and make it like this. All right. So this is the numerical representation for these amino acids. But this is a very arbitrary assignment, right? So the fact that R comes after A doesn't really match up with any scale. So these are arbitrary numbers assigned to each letter. Okay. So the numbers 1 to 20 really has no meaning other than it's a one-to-one assignment. If you are encoding something and feeding it to a neural network, you want the numbers to really mean something. Okay? So instead of these numbers 1 to 20, you can, for instance, use the hydrophobicity of each of the amino acids. So you can take each of the amino acids and replace it with how hydrophobic that amino acid is. All right? So that would be more meaningful. So that's one, taking amino acids and representing them as their features is one way of dealing with this. Another way is to, instead of representing each amino acid by a single number or by a single feature, you can represent it by 20 features. Okay? So if you think about the positions in your sequence, if you have an A here, the fact that you have an A will be your feature. Okay? Or the fact that you have an R there will be a feature. So our features now, instead of being like hydrophobicity or electrostatic potential and so on, will use the features of being an A, being an R, being an N, and so on. Okay, so we'll have 20 features. So if you have your sequence like this, we'll create we'll create 20 rows, and each column will represent one of these residues. Okay. And each row here is going to represent whether or not we have an amino acid there. So we'll have a 1 here, zeros everywhere else. We'll have a 1 here, zeros everywhere else. Okay. 1, 0. Up, and then we have a 1 for A and 0 everywhere else. Okay. So now we no longer, we don't really care about how these amino acids are ordered. If A had a different assignment, let's say 20, in the way that MATLAB encodes amino acids, we would still get the same sort of same layout. All right, so A will consistently be assigned as a 1 wherever you have an A. All right. So once you have this numerical matrix where each column is represented by a vector, right, by a vector of numbers, then each column becomes a sample for you. So what that means is whenever you see a column of this data, you can make predictions with it. In the simplest case, where we take a window size of half window size of 0 as described in the problem, we are using just a single column from our sequence, and that just encodes which amino acid we have there. All right. So we have these samples. You can consider them separately, or you can consider them as a large matrix. And each of them will have just a 1, 1, and zeros everywhere else. So in the problem, we also have a secondary structure corresponding to this sequence. Let's say it's H, E, H, and so on. Okay. So for each of these columns now, we also have an additional encoding that we can do, and we'll follow the same idea. Actually, let's do it differently. No, we would use the same code. So the fact that we have an H will give us a 1 for that row. I think this was a P in the problem. And the fact that we have an E in the second row will mean that we have an 1 in the second row here, and zeros everywhere else. So we are using the same encoding scheme for the outputs that we are trying to generate. But now we have our alphabet size is just 3. Okay. So helix, sheet, or a turn. So now for each column we have another vector where we have the correct output for that residue. You have a single 1 and then 0. Okay. So what we want the neural network to do is, given this vector, a vector like this, we want it to generate us a vector like that. So whenever you give a vector of size 20 with a single 1 in it, you want to generate a new vector like this. The neural network outputs will not have a 1 exactly. It will be a continuous output, but you can apply a threshold, or given 3 outputs, you can just use the one that has the maximum value. Right. Okay, so now I'm gonna stop the coding here and move on to a description of neural networks and get back to the implementation. All right, so the idea of neural networks comes from the biological neurons, where they are being fed inputs, and if that input exceeds a certain threshold, they get activated and they fire their own output. Okay. So you have these inputs. Each input has a weight. All right. You multiply the input with the weight. You add them up. If it exceeds a certain threshold value, then you get an output. Okay. So that's the main idea. For the neural networks, you have, again, inputs, weights, you multiply them, you add them together, and then you apply an activation function. Okay? So for the biological neurons that I described, the activation function is a step function, right? So if it's above a threshold, it's a 1. If it's below, it's a 0. But you can have more different step functions different activation functions to give you a continuous output instead of a 0, 1 output. All right, so some of the common activation functions are the sigmoid and the tangent function. And the reason that they are most commonly used is that it's easy to take their derivative. And I'll tell you why being able to take the derivative is important. So once you have these individual neurons, you can stack them together where the output of one neuron feeds into the input of the next layer. And you can structure them in these layered structures instead of having a chaotic structure. You would usually have a layered structure where your inputs will feed here. So these will be your input vectors. In our prediction case, you'll have 20 vectors, 20 numbers, where one of them will have a 1 and the others will have a 0. Okay? So that will be your input vector. Those are fed into a hidden layer. So each of these is a single neuron. They take their input, they have weights. The inputs are multiplied by the weights. And then an activation function is applied, and they have their own output generated from that activation function. And the outputs of those are combined at the next level, and so on. But at each neuron, you always do the same thing. You take its inputs, multiply it by its weights, apply the activation function, and generate a single output. Okay. So the result of this is going to be your HET predictions. So that the output is going to give you the predictions that you are looking for. All right. So here you have this sequence, this protein sequence. If you look at just this I, we encode it using our encoding scheme of just having a 1 for that amino acid and zeros everywhere else. So your input is going to be 0, 0, 0, 1 all the way. The rest are 0. So the third input node is activated, right? And then the output layer will generate numbers that correspond to the prediction from this neural network. These are going to be continuous outputs, and you would take the one that's the largest and use that as neural network's prediction. So for this example, for this example figure, the neural network predicts this I to be an alpha helix. All right. So once you make predictions for each residue, for each amino acid, so this is not part of the homework, but in general, you would also want to go over the predicted residues and combine them into sort of an improved prediction. Let's say you made a single residue prediction and you got things like HE, 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 right? So you predicted individual amino acids, and your neural network outputted a helix for the first residue, a sheet for the second residue, a helix for the third one, and so on. Okay, but this is not a very biologically reasonable way of arranging secondary structures. They usually come in segments, right? So a helical residue by itself doesn't really mean anything. A helix is defined as a regular structure that makes hydrogen bonds with other residues that are also part of the alpha helix. So you can take this and feed it to a second layer neural network that will fix that problem. Okay, so in a way, it will look at just these and compare them with the correct output that's part of the training, and learn how, given predictions from the first layer, learn how to rearrange and make changes to match a biologically more reasonable assignment. Okay. So your first layer, your first level neural network would make predictions at 3-state output, and you would take those predictions, and just like you mapped the amino acid sequence to a 3-letter alphabet, you can take the predictions and then map them to another level of predictions. All right. Let me jump to how we actually train the neural network. So neural network is usually used as a black box. All right, so you provide your inputs and known outputs, and you train the network on these known outputs. After the network is trained, then you can give the network previously unseen samples. So you can give the network new samples that it has not been presented before as part of the training. And it can make predictions on those new inputs, and then you can evaluate its output based on what the correct answer should be. So if you know the correct answer, you can evaluate it. In the real life scenario, you would use the neural network on cases where you don't know the answer. All right? So that's the ultimate goal, being able to make predictions for things that you don't previously know. But then you won't have a way to confirm the results. You just have to rely on what its performance has been for the things that you need. So how do we train the neural network? Training the neural network involves finding the weights into the into the neuron units. Okay. So everything else was provided, the inputs, the numbers that feed into the network. So the only thing that the network needs to adjust are the weights so that it gives the correct output. So the training involves you give the inputs, the network gives you an output from its current weights. And then you compare the output with what you should get, and then go back and adjust these weights. And you do that over and over until you are satisfied with what the network gives you. And you don't want to adjust weights randomly. You want to sort of direct yourself toward the correct answer. And the way that we direct ourselves to the correct answer is a method called gradient descent. In the gradient descent, we have an idea of the direction that will take us to the best answer, to a better answer. And we move the weights, we change the weights in that direction. Okay. So we increase or decrease each weight by an amount that we think is going to improve its result. And I'll explain what backpropagation means. All right, so let's say we have this curve. All right, so this curve represents the error of a function. Okay, so where the minimum is here, so we want to end up here. And we have some parameters to adjust. The parameters are is this R, or the error is the R. So if you take the derivative of this curve, you'll be pointing in the direction of increase, the largest increase at that point. So at any point, if you look at the tangent, it'll take you in the direction that where its value would increase the most. What we'll do is just take the negative of that and move in the opposite direction. So let's say you are in a place where there's a lot of fog, and you want to find the lowest valley. You want to find the lowest place in that landscape. So the best thing you would do if you cannot see too far ahead of you is, let's say at each step you can only see like a few meters in front of you. You would look around, find the direction in which, find the direction that takes you to the lowest the most. Okay? And you would walk in that direction. And you would repeat that continuously to end up in a low altitude place. It's the same idea. It's a local optimization technique. At each step, we only have an idea of what the value is going to be at that local neighborhood, but we don't really know what the function is like at the global scale. All right, so we repeat this step over and over until we are satisfied with where we are. Okay. So once we find the direction that we need to move in, we multiply that by a constant factor. and then we multiply that much. That constant factor is usually called the learning rate. Okay? And you don't want the learning rate to be too high, because if the learning rate is too high, let's say you found out that you need to move in that direction, but you multiplied, let's say, with 1,000, and it takes you all the way here. All right? And then you would then figure out that you have to move the other way, and then it will take you back. All right? So if your learning rate is too high, you'll be jumping back and forth around the minimum and never getting to it. At the other end of the spectrum, if your learning rate is too small, then your step sizes will be very small, and it will take you a long time, computationally, a long time to end up at the minimum. So learning rate is an important parameter that needs to be specified, and it should help you get to the place that you want in a reasonable time without making very, very high jumps. Okay. All right. So given sufficient power to your neural network, you can represent any function. So there's a theorem that for neural networks, that if you have a nonlinear activation function, or if you have so if you in a multi-layer network, given sufficient number of hidden units, you can have it represent any given function. So it can learn any function that you can specify. All right. But what it will do is it will memorize the function, right? So you don't want the network to memorize your inputs in a way that it's only able to give you the correct answers for your training data and not be able to generalize to your test data. So you want the neural network to learn the rules that map the biological rules that sort of cause the protein fold into a secondary structure state, instead of just memorize the mappings that you have for the particular set of input, for the particular set of training data. So this figure shows the number of iterations over at training the neural network. So the epoch just means that you've iterated that many times. So you take all of your training input, you present it to the network. That's one epoch. Okay? Then you go over again, you present it again. And you adjust the weights at each iteration. And as you do that, your training accuracy increases, right? So your network is performing better and better on the training data. But on a test set that you never present, that you never let the network to learn on, so you never let the network adjust its weights based on the test data. All right? But you still check the performance of the network on the test data. So you feed it to the network, you look at its output, and you independently look at how accurate it is. And then you get the blue line where the accuracy increases for a bit, but then it starts to decrease. All right? So this is where, let's say at this point, your network has really stopped learning in the sense that you want it to learn. Okay? It performs better on the training data, but doesn't really do so good on being able to predict new unseen data. So you don't want to overtrain, you want to be able to stop at a point where the network will perform well on test data. So to do this, what you usually do is you take all of your known samples and you divide them into different sets. We usually divide them into training, testing, and validation set. Okay? So let's say the validation is here. And we keep training the network until the performance on validation doesn't improve anymore. Okay, so this is the point, and we'll use the weights of the network at that point as the final learned network. And then we'll use this for any future prediction. And then you would also have your test set that you can use to report your performance. All right. If usually, I mean, if you are reading a paper or reviewing a paper, this is one of the things that you need to look out for. So make sure that you look at how they separated the input and output, the training and test sets. Okay. What's the question?
The validation set, does it have the properties?
Any property? Okay. So the validation. So everything should sort of be as homogeneous as possible, right? So you want each of these sets to, in a way, represent the overall distribution of proteins. Okay. But there's one property that that you need to consider within each set and across all of your data, and that is things should not be too similar to each other. So let's just consider sort of a trivial method for prediction. Given and let's say you are allowed to memorize anything you want, or you can look up past known inputs. So if you are presented a new sequence, you can just see if you've seen it before, and if you have, you can output the secondary structure states that you had for when you've seen it before. Okay. And if things are too similar to each other, then you can do that more, right? So if you use sequences that are highly similar to each other, then you are using this similarity effect more often than not. If your overall data set contains sequences that are highly similar to each other, let's say this block is 95% similar, meaning 95% of their residues are identical. And as a second block, you have 90% similar. And even though you are taking your entire data and separating it into three sets randomly, you are still using things in your training data that are highly similar to your test data. Okay, so it's not a very fair way of separating out a test sample, right? Because your test sample is already, in a way, present in the training data. So to overcome this similarity effect, what they usually do is take your entire training sample or entire data and reduce it by sequence identity. So they take all known structures where you have a known secondary structure state, and they filter those out in a way that you end up with sequences that are not similar to each other than, let's say, 40% sequence identity. All right? And that would usually be denoted in these methods. They would say, we took a data set that's 40% sequence identity redundancy. Okay, so in a way, the set of sequences is non-redundant. Okay, so they are not redundantly similar to each other. Okay, so let me go back to the coding now, and we'll encode the sequences. All right, so our encoding, let me first describe the half window size of 0. We take a sequence, an amino acid sequence, or it could also be a secondary structure string. We apply the same encoding scheme to both input and output, and we return a binary matrix, okay, where for each residue you would have 20 numbers. One of them is going to be 1, and the others will be 0. That's for half window of 0, okay? So here what I do is I look at my sequence, For half window of 0, it's trivial. You just fill in a 1 for the amino acid that corresponds to what this amino acid is, and you have zeros everywhere else. Okay. For half window size of greater than 0, so let's say half window size equals 2. Then that means I'm looking at 2 residues to the left and 2 residues to the right of each central residue that I'm trying to encode. So let's say I'm encoding this residue here. I'm going to include two additional residues on the left and 2 additional residues on the right. So I end up with 5 residue window. Okay. So this 5 residue window can be encoded by 5 times 20, which is 100 numbers. So I will have, instead of 20 numbers that I had before, now I will have 100 numbers that correspond to this central residue. The first 20 numbers is going to be the encoding for this first residue. Okay. The second set of 20 numbers is going to be the encoding for the second residue. The third set is going to be the central residue, and so on. Okay. So you are combining, remember the half window size, when the half window size was 0, you only had 20 numbers per residue. When the half window size increases, you are using the neighbors also to encode a central residue. So you are using their vectors and just concatenating them together. Right. So each central residue is now represented by what's also around it. And why do we do that? It's because in protein folding, residues, the way that residues fold isn't just determined by what amino acid you have. It's also dependent on what amino acids are around it. Right? So, for instance, if you have a regular structure of hydrophobic bonds, you need to have a coordinated folding of all of those amino acids involved. So things that are around each central residue is effective on, is a determinant on how it should fold. Okay. All right. Let me just move on to training network. Okay, so in this function, I'm giving the amino acid sequence, the secondary structure sequence, the half window size, and a previously trained network or the number of hidden units. If this is a numerical value, okay, then I'm creating a new neural network with that many hidden units. If it doesn't exist, if this parameter is not provided, then I'm creating a neural network with 5 hidden units. The larger number of hidden units you use, the more powerful your neural network is. And the more powerful it is, the better it can learn, with the downside of memorizing your training data. So if you make it too powerful, if you use too many hidden units, it will learn your training data very well, but it will not generalize to test data. And the question was asking you to specify the amount of training data and the validation data that you are using from the training set. And since we have a separate set, a separate file that we will test on, we set the test ratio to 0 so that we can provide it by hand. Normally, when you use the neural network, you specify, you just give it a complete data set and it'll split it into training, testing, and validation. But for the homework problem, I asked you to use a separate test file so that we don't have to do it randomly and we can repeat the training, testing, and test on the same data set. Okay, so we encode the sequence. Our alphabet is 1 to 20. And then let me do this. So I'm going to read it. So I have it here. Let's just look at what A looks like, the first 10 amino acids. SS 1 to 10, you have those. Let's encode them. I'll just encode the first 10 amino acids with a half window size of 0. It'll be a large matrix. Yes. Let's look at this matrix. Let's look at the first 10 rows and the first 10 columns. I don't have that many. First 5 rows. An empty matrix. Oh, I have an error there. 120. All right, so this is encoding the first 5 amino acids, right? The first row stands for A, the second row stands for R, third row N, fourth row D, okay? So you have a 1 for A here, and then 1 for D in the second position. L is somewhere down that I am not printing, and then D in the last position, okay? Right, so you take your amino acid, you encode it in this binary format where each row represents an amino acid. If you use a half window size of greater than 0 or a window size greater than 1, then in addition to encoding this amino acid here in this first column, the first column will also have the encoding for the second amino acid. So you would just take the second column and put it at the bottom of the first column. All right. So that's how a window size greater than 1 would be encoded. So we would repeat this for the secondary structures, and that's going to give you the matrix Y. And the idea is the same. Now, instead of having 20, your alphabet size of having 20, you have an alphabet size of 3. You have the H, E, T, okay, which are the secondary structure states. And let me just copy and paste these. F9. So we create network. Get these. Okay. And then when you train the network, what you are doing is you are taking your input matrix and the output matrix and giving those to the neural network. Okay. And you will see this GUI graphical interface unless you turn it off like this. So if you don't like to see that graphical interface, you can turn it off. And once it's trained, you can look at its performance, and it will show you a plot of training, validation, and the best case. Right. So once we've trained the network, then we read our test data, and then we will test the trained network on the test data. Let me repeat this. And you can look at its performance. Okay. So the training and the validation looks like they are performing in the same way. And the error is measured in terms of mean squared error. So our outputs contain 3 outputs, right? So the HET, one of them will be 1 for each residue. And the error is described as if you have a 1, but you have a 0, you take this, you subtract it, you square it, and then you add all of the errors for all 3 outputs, and then you take the square root. Or you don't have to take the square root if you just want to plot it. It's the mean squared error that the neural network is minimizing. So the error that the neural network is improving at each iteration is the mean squared error of the outputs compared to the correct outputs. Once you've trained the network, you can use the network to test a new data. So in this testnet function, you're not being told the half window, you have to determine it from the data or from the network itself. Okay? So you determine the half window, you encode the amino acid sequence, and you predict by using, where's the net? Oh, here it is, okay. So you take your amino acid, you encode it. So this is just the X. Let me just take that out and write it explicitly here. X equals that. So this is the same thing that we did for the input sequences. But now if your network is trained, you can just use it as if it's a function and give it the input X. It'll give you the predicted output Y. But your predicted output is going to have 3 outputs, right? 1 for H, 1 for E, 1 for T. And you want to consider the one that has the highest value as the network's prediction. So the network is not going to give you 0 or 1, it will give you a continuous number between 0 and 1. And we'll just take the one that's highest and consider that as 1 and consider the other 2 as 0. So that's why we take the maximum of these numbers, and then we use that as an index into this alphabet. So Y up to here is going to be a number 1, 2, or 3, right? 1 is going to be H, 2 is going to be E, 3 is going to be T. And we index into the alphabet using those numbers. It's going to give us a string, which is the prediction. Okay. So let me stop here and show you how it works. F9. Okay, so we encoded X, we get Y. Y is 3 rows, 35,000 columns. So our sequences, when we combine them all together, we have 35,800 residues. And we apply the max function, we'll get a single column, we'll get a single vector, and it'll have a prediction for each residue. Okay? And the index is going to be used to convert those numbers back into a sequence, back into a string. So that's our prediction. Okay? So the first 10 of them are like that. So this is a T, that's an H, 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 E, T, T, and so on. And if you just use alphabet sub y, you'd be getting the corresponding letters. Okay. All right. So once we have the predicted secondary structure states, and if we know the correct output, we can compare them and report their Q3 score. And for this example, the Q3 score was 47%. Okay. So just by using a single amino acid information, we are able to predict the secondary structure state at a 47% accuracy. So is that good or bad? What would the random, if we just assign randomly, what would the accuracy be? 33%, right? So if you look at a residue and just randomly say it's an H, or randomly say it's an E or T, you have a 33% chance of getting it right. So we are performing better than randomness. Okay, so that's good. When you are using a single amino acid information, it's sort of the same as using the secondary structure propensities of amino acids. So a more educated guess would be looking at your data. If, let's say, whenever you see an amino acid A, you've already know that A likes to be in alpha helices most, right? So whenever you see an A, you will say it's an alpha helix. Then you are increasing your accuracy. Okay, so you are assigning things to the secondary structure state that they are most seen in. And if you are using a neural network that's trained on an individual residue, where your half window size is 0, so you are only looking at the residue itself without its neighbors, then it boils down to the same statistics. The neural network will learn how frequently each amino acid likes to be a helix, a sheet, or a turn. All right, so let's repeat this, but now use a half window size greater than 0. And see the accuracy. Copy paste that. I'm going to turn off this graphical interface. Let's do the half window size of 1. And then let's run it on the test and get 54%. As we increase the window size, we usually expect the accuracy to increase. Okay. All right. So this exercise has two calls to the test function. One of them is on the training data. So this will be the same. It will show you the same result as you see on the performance graph of the neural network. But the performance graph of the neural network will be the mean squared error. So the neural network doesn't really care whether it gets the correct outputs, the correct secondary structure state correct. It'll worry more about the actual number, right? But what you care more is which one has the maximum value. So that's why we have our own test performance function that takes the neural network's output, looks at which one is the highest value, and looks at the accuracy of that. So if we do this, just read this again, apply it here, 55%. So our network performs 55% accurate on the training data and 54% on the test data. You can get this arbitrarily more accurate So you can get that to 100% if you want by using a larger and larger number of hidden units. So for this example, we used 5. So let's use 50 and repeat this. F9, F9. The more hidden units you use, the longer it'll take for the network to train, usually, because you have more weights to adjust. So this may take a while, but the resulting network is expected to perform better on the training set, okay? But not as much on the test set. But because we are using a data set that is non-redundant, we are less likely to hit into that problem. And the fact that we are also using a validation set within our training makes it safer. So if you don't use a validation set, then you are more likely to run into a scenario where you are learning your training data better and better, but your test is not performing so good. So I'll let that run for a while and look at the other problems on the homework. Okay, let's look at the SSB stats. Oh, it's done. F9. So training, we performed poorly, 48%. Let's look at the test. 47. Well, it didn't perform as I thought it would. Let's just turn this off. Let me repeat this. F9. I'll open a new MATLAB window. All right, so in this problem, what we're going to do is we're going to use statistics, basic sort of frequency to see which amino acid likes to be in which secondary structure state. We take the amino acids and their secondary structure states, and then we iterate over for each amino acid. We find the locations where that amino acid is present. Let me go step by step here. F5. So we'll output a 20 by 3 matrix where each column represents the likelihood that each amino acid will be one of the 3 secondary structure states. So we are looking at the amino acid alanine, which is represented by a 1 in MATLAB. The AA is an amino acid sequence. So the first letter is A. It helps, it's usually faster to work with logical vectors. So I contains a logical vector of zeros and ones, where you'll have a 1 whenever you have an A in your sequence. Okay. All right. So you have this I that represents the A in your sequence. So you have a 1 here, 1 here, 1 here, and zeros everywhere else. Okay. Then we look at our secondary structure string. And we create a logical vector for the helices. Okay. All right, so let's say these are helices. H, 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 E, E, H, H, E, E, E. So one way of doing this is to say SS equals H, right, and then AND that together with I. That'll give you the intersection of the two. It'll give you the number of times that you have an A that's a helix. What I'm doing here is slightly different. I'm using I to index SS first. So I'm picking out from this string SS only those entries where you have a 1 here. And that already will contain alanines that are helices. So I don't do this, I just do this. Right? And the number of those is going to be the number of times that alanine is in helix. And I divide that by the number of times that I have an alanine. As a result, this number will contain the frequency of alanine being a helix. So what percentage of alanines are helices? And I repeat the same thing for beta sheets and terms. And when I'm done, I will get a matrix. Let me just show you the first 5 rows. The first row stands for the alanine. The second row stands for the arginine. So it's the way that MATLAB orders amino acids because I used this into AA function. The first column is alpha helices, second column beta sheets, third column is terns. So alanine likes to be in a helical state the most. 46% of the time, it's a helix. Arginine is a turn 43% of the time. Okay. So I've taken the set of known secondary structure states for my training data and constructed this 20 by 3 matrix. And the question was also asking you to plot the frequencies for helical structures. So you just do a bar graph like that. And it's nice to make the X tick labels represent amino acids instead of numbers. And to do that, you just use the X tick label property for the axis and give a cell array of the strings that you want to use for the X labels. So I took the X-axis and set the X tick label to be the amino acids themselves. And these are the alpha helical likelihoods or frequencies for each amino acid. So A likes to be an alpha helix, E likes to be an alpha helix, and so on. Okay. The last homework problem was asking you to predict the secondary structures by these frequencies. So what would be convenient to do is to take this matrix and collapse it into a single vector. Let me say F5. So I have my matrix. If I use the max function, and this is how you would use the max function if you want to obtain a column as a result. So I'm taking the maximum along each row. This will give me, oh, it didn't give me anything. Max. This will give me a column vector of the values that are largest. but I'm really more interested in the location of these numbers than the numbers themselves. The max function gives you a second output. So I'm not interested in the first output, I'm interested in the second one. And that will be the locations of these highest numbers. So for the first row, we just look at the first 5 again. And I want to 5. So for the first row, the first number was largest. For the second row, the third number was largest. For the third row, the third number is large again, okay, and so on, okay? So I now contains a value for each amino acid. It's a value between 1 and 3, and it'll tell me which secondary structure state each amino acid likes to be in the most. If you like, you can convert this to letters. So my alphabet is HET, and I'll use this I to convert that I vector into a sequence. So you'll have 20 letters here representing what each amino acid likes to be. Let me just start this function SSP predict by stats. Let me call this thing AA to SSE. So you did the things that I did above, and you got that this matrix right here, or that vector. Then you can take your amino acid AA, convert it to integers, AA to int. So that will be numbers between 1 and 20. So you take your sequence and convert it to a numerical representation. And then you can index that AA to SSE, and it will give you the predictions per recipe. Let me repeat this again. RAT equals that. Equals, what was I? How do I view the history? Oh, here it is. I did that. And I have my alphabet. And then I'm just avoiding using for loops using these indexes. Okay, and then this is going to be my prediction. Just go step by step and show you what happens. SSP predict by test. Let's say we have a sequence like this. Ignore the plot. So we collected the stats, which is a 20 by 3 matrix. We looked at the maximum values and figured out which column has the largest value, and used that to generate secondary structure states instead of those numbers 1, 2, 3. So AA to SSE is a mapping from an amino acid to a secondary structure, and then pred is the prediction for the given amino acid sequence, where A will always be assigned to a helix. Okay. All right, so that's our prediction. The question also asks you to go through this assignment, and if a loop residue is surrounded by two alpha helical structures, you are asked to change the loop residue to an alpha helix. A simple way of doing this is to use the str find function. Let me construct my prediction here. Just create a fake prediction. The str find function will give you the locations of each such example. And then you can just replace them with an H. So it's that simple. And then in the second pass, we do the same thing for loops that are surrounded by helices, where this needs to be a T. We replace all T's with E, H, H, H. No, hold on. All right, so let me repeat this. The str find function will give you the location of the match for this string. Let me fix this string. So E is a T. So a loop is a T. The question asks you to replace any T surrounded by two helices with a helix. Okay, so we don't want a term by itself, essentially. The str function will give you the locations of these hits, but it will give you the location of H, right? So you want to change the T, not the H. So you'll just add 1 to this. It'll give you the location of T. And then you can just index pred and set that to become an H. Plus 1. So any turn surrounded by two helices is replaced with a helix. Any turn surrounded by two beta sheets is replaced with beta sheet. And finally, any single alpha helix or beta sheet is replaced with a loop. All right, I'm not gonna give you the 100% accurate answer, but let's just use regex replace function. We're gonna take the prediction and we'll look for not an H, so not a helix, and then a helix, and then not a helix. So we're looking for a helix surrounded by non-helical secondary structures. And we'll replace that with a term or a loop. But we want to preserve these non-helical places, right? So you could capture them. And then we need to replace it like that. I don't know how to do it in MATLAB. Here you go, this is what I want. Expression, it's a dollar sign. So $1, $2. So this $1 will be whatever this expression matched. So if it's an E, then $1 will be an E. Okay. So this is equivalent to saying string replace. In prediction, if you see EHE, replace it with an ETE. But there are more than one case like that, right? So if you see an EHT, replace it with ETT. So I'm looking at the middle residue. If it's always a helix, the one surrounding it is going to be a non-helix. And I'm only modifying the one in the middle, changing it into a T. So instead of writing all the cases like that, I have this regular expression that captures anything that's not an H. And I'm preserving it. And then anything that's not an H, I'm again preserving it. And then the H itself is going to be replaced with a T. Okay? All right. I told you that this is not a 100% accurate solution because it doesn't handle the beginning and the end of the sequence. But let's not worry about that. We do the same thing for beta sheets and replace them with a T. So let's repeat this prediction and see what its accuracy is on the test set. F9. Prediction equals I got an error. Right, so there are some problems here. Some of the amino acids have values greater than 20. So let's just set them to become ones. AA greater than 20 equals 1. We should really ignore them, but let me just do a quick and dirty solution here. We have a problem again. Oh, must be an A. Right, so now I have my prediction. So I get 48% accuracy on the statistical. Okay. All right. 11:30. Let's take a short break and then we'll continue. Any questions about these implementations? No? Okay, this one. I was going to show you the performance on the neural network with 50 units. It's done. 48%. 48%.